My name is Aonghus Lawlor. I work in Insight Centre in UCD. And this is kind of a high-level kind of an overview type talk. So we're kind of, there's a lot of people, I guess, in Insight that are using deep learning techniques in various guises. We're probably not, I guess, at the cutting edge of research in terms of developing the next stage of these kind of deep learning techniques, but we do use them a lot and we find a lot of interesting uses for them. So just to kind of say that this is really about text, and I guess most of you, if you're kind of working in this area, you'll be dealing with text in some form or another. So I want to kind of give a high-level overview, conceptual overview of some of the techniques that are important when dealing with text. And I guess at Insight, a lot of people, a lot of the researchers in Insight are dealing with text in some form or another. So this is kind of where these problems, when you're dealing with text, are always cropping up. So if you're doing any kind of search engine, any kind of search query, you've got to understand the text the person writes in order to be able to process it in some way. You've probably seen Watson, IBM Watson. They've developed some pretty cool kind of question and answering type technology, which again is hinged on understanding the text, semantic understanding of the text. Machine translation, which I guess Google are kind of famous for. Again, there's a lot of very important kind of semantic understanding of language models that goes on behind that. Some of these other techniques here, like Siri and Google Now, that are again doing speech recognition and then turning it into text and developing some sort of, I guess, actions or understanding the intent of the user based on turning the speech or the sounds into text. So again, it hinges on some sort of text understanding. And again, you can kind of see some of Microsoft's, maybe some of the more successful and some of their failed efforts down here with these little chatbots that they've tried. So you can see that again, the importance of how you train these models. So Microsoft, they again trained all these wonderful deep learning networks, released it on the internet, and of course people trained it within a day to say some very nasty things. So again, it's the importance of training and understanding your models and how to use them is really important. So again, I think I was talking to Bojan, I don't know if he's here. This is, again, an example just from 2010. Twitter Mood predicts the stock market. So this is an example where people were pulling down kind of tweets and then looking at the tweets to try and understand the sentiment. And again, this highlights one of the important ways in which we try and understand text, which is to understand the sentiment. How are people saying? What are they talking about? In what sense are they talking about? Is it positive? Is it negative? What they found, and some of these results may have been called into question, I think, in later times. But what they seemed to find was that the Twitter Mood kind of predicted the behavior of the stock market. And I think it was lagged by about 3 days or so. So again, this kind of represents something like the kind of collective intelligence that the market is reflecting people's overall feelings of happiness or confidence or whatever it is. And again, in order to understand this and tap into it, you've got to be able to understand text. And again, these are the futures. So something that we work on is recommending hotels, understanding hotels and travel. This is an application that kind of people are working on, which is, I don't think this exists as of yet. But a lot of people would like it to exist. And again, you can just kind of tell your phone by typing it in, or they speak it into something like Siri or Cortana. You can give it an instruction to say where you're going, and it'll look for flights for you. Okay, so again, this kind of requires a very high level of understanding of the text. Again, here's just another example where it's able to pick out from very kind of abbreviated labels for the cities, where you're going from, where you're going to, things like dates and times. And it was a very, very difficult job to do, but it's something that people want. They want to have this kind of level of understanding of text. And again, you're going to be seeing, I think, in the summer, Google, I think, have announced, I don't think the app is available yet. It's going to be popping up in your Hangout, whatever chat client you use. It'll be popping up from Facebook in your inbox as well. These kind of prompts, which I guess are analyzing what you're typing, how you interact with people in your social network, and then prompting you using some sort of artificial intelligence based on top of the semantic understanding for how you should respond to them. Okay? So again, I think this was from the Google demo that they released. I think they're going to release this after. So we'll see how it works. I haven't tested this. It's just a screenshot. It may not actually work, and people may not appreciate it, but we'll see. And again, the reason why we're interested in it is because we work in the recommender systems group, so we're trying to recommend items to people. We focused recent times on things like hotels. So the way we do that is to look at user reviews. People write a lot of reviews of hotels online. They're usually very rich reviews. They talk about a lot of features of a hotel, and if we can understand the features that they're discussing and the sentiments that they apply to those, so if they like, for example, room quality or the service or so on, we can make better recommendations to them. So again, this kind of hinges on a very good understanding of text. So some of the things that we're always working with, we've also worked with news recommendation as well, so trying to recommend news articles, in which case we're looking at kind of extracting information from the news to see what was in the news, what things were of interest to people, building user profiles, name identity extraction, part of speech tagging, all these kind of standard NLP techniques are kind of core to building a good news recommender system. When it comes to hotels, again here, these are just some of the kinds of things that people are saying here about the hotels. So we're kind of always writing these reviews, and some of them are quite rich. So our job is to try and understand the precise details of what they're talking about in order to make better recommendations for them. So again, it fits into the field of natural language processing, opinion mining, sentiment analysis, and then building kind of analytic tools, recommender systems on top of that. So what we kind of want to understand, we want to be able to take the text, pull out the features that people are talking about, the sentiment that they've applied to it, understand, I guess, in some sort of high level, the topics or the things that they're talking about, and then have a better understanding of the sentiment. So this is, again, something we pay a lot of attention to, better sentiment analysis techniques, and that's something where deep learning can really help us. And there's a lot of companies that are doing this, and they do different parts of the process. Some of them do it better than others. So this is a company that's kind of, I guess, doing a little bit of kind of very basic sentiment analysis, a little bit of topic extraction. And again, we'll see some techniques for extracting, for doing that a little bit better. These are some of the papers. So again, the reason why we're interested in deep learning is that there's a huge amount of, I guess, kind of crafting that goes into sentiment analysis and pulling features out of text. And deep learning kind of promises, or makes the promise, or makes the claim that you can kind of do away with a lot of this kind of hard work of handcrafting your feature selection. This is the really hard part. And people have spent decades in the field of natural language processing trying to build really complicated and advanced and elaborate rule-based systems for understanding text, understanding the relationships between words, and using that kind of understanding then to build, to kind of get semantics out of text. And deep learning kind of promises to kind of do away with quite a lot of the hard work that we did. So no more handcrafted features, right? This is the kind of promise of it delivers on that or not, I'm not sure. It maybe swaps one set of problems for another. And of course, part of the reasons behind it is that we can kind of learn these kind of deeper intermediate layers. So again, the work kind of started off in deep learning from trying to understand images or do kind of image recognition. You can kind of see here how they're building up more sophisticated features as you kind of add more and more layers. So again, this is where the initial work on deep learning came from. And I suppose it's fair to say that deep learning techniques have kind of beaten state of the art in quite a lot of areas, and often by really significant amounts, or by significant distances. So things like language modeling, so I'll talk a little bit about word-to-vec, image recognition, sentiment classification as well, speech recognition, handwritten digit recognition. All these areas, deep learning is kind of taking a very general approach and going far beyond what was previously possible. In many cases, getting to kind of human-level accuracy at many of these tasks. In natural language processing, these are some of the areas where people are applying deep learning models and doing them quite successfully. So you can see here, again, sentiment analysis, automatic summarization is something, again, that we're kind of interested in when we're building recommender systems. It's nice to be able to summarize a review, or if you're building a news recommendation app, you probably want to summarize, to get a title or a little snippet. Things like parsing, information retrieval, machine translation, topic segmentation. Again, these are all areas where deep learning can help out. So how do we do it? The basic ingredients, the starting point, is what we call word representation. So we've got to have some sort of a way of representing the basic element of text, which is a word. We'll see how you can actually go a little bit lower than that to characters. But for a start, this is kind of where we start with words. So the basic elements of text are used. And in vector space, we kind of represent this as a kind of a one-hot representation where you've got a vector which is the size of your vocabulary, and basically you switch whichever particular index corresponds to that word is switched on, that corresponds to the vector for that word. The problem with this approach is that if you try and combine these word vectors for different words, it's very hard to measure some kind of similarity between them, right? Because you've just got one index is on in one word, and it's in the rest of them. So something like a cat, for example, cat and a dog are quite similar. They're conceptually very similar. They're both animals, mammals, and so on. But you don't get any of that kind of similarity from the one-hot word vector. So the basic idea of natural language processing, or statistical natural language processing, is that we can understand the context of a word if we understand the words that are around it, so the words that are commonly used in association with that word. And this is the distributional hypothesis. So it's derived from the semantic theory of language. And it basically says that words are used and occur in the same context. They tend to have very similar meanings. Right? So we'll see how to use this. Here's an example where we're talking here. These are just extracts of text. So the keyword here will be banking. And again, we can see that if we look at the context or the words that are before and after banking, we can see then words like crisis, government debt problems, Europe, unified regulation, and so on. This is the context. These words represent the context for banking. Now we can get different views of this context. So if we take a very, very small window, we tend to focus on the syntactic details of the context, right? If we expand the window quite a bit more, then we tend to get much more of the semantic representation of the context, because we're pulling in many, many more words that are far distant from that. And I guess so when we combine these vector space semantics with some sort of prediction, the basic idea here is that we want to represent this word as a word vector. So we want to represent it in some sort of a lower dimensional space than the vocabulary space. So usually when people are building these word representations, they tend to turn these word vectors into some sort of a feature space where the features are, the word vectors are features. But generally the dimension of that space is reduced to somewhere between 200 to about 500 or so. So it's a much, much smaller dimensional space. And again, the elements of these vectors here, so this should be something like 200 or 300 dimensional vector here for cat. And these are real valued. These are vectors in real space. So again, this is the kind of the word representation. If we can represent vectors and we can learn these representations in the space, we can do much more interesting things with them. And the idea is that, again, by similar words being close together, this allows us to generalize from a sentence to a class of similar sentences. So you can see here that the wall is blue or the wall is red, but the context is kind of the same. So if we can learn from that context, or we can learn from the context this kind of meaning, we get some sort of semantic understanding from the fact that the contexts here are very, very similar. And this is a visualization of word embeddings that come out of a neural network. So again, I'm sorry if you can't see them here, they're very, very faint. But here on the left, what we found are these word embeddings for numbers. So you can see here that we've got 5, 6, 10, half, few, several. So these are words that represent numerical quantities, and in some cases numbers. On the other side, we've got words that are related to the stock market, to the business, and finance, and so on. And so what we're seeing here is that when you perform this kind of word embedding, or if you can do it properly, in this case, this is another, these are words, and the closest words using a Euclidean distance measure in this embedding space. What we see here is that these are actually pretty good representations of similarity or similar concepts to the initial word at the top. So what we've done is we've kind of queried this word embedding system that we've developed. I mean, you can see here for the country France, we're getting other countries, Austria, Belgium, Germany. These are countries that are actually close to France, or Germany, are very, very similar countries. So we're seeing that we're getting conceptually similar words that come out of these word embeddings, again, using context. And what we can say is that these representations are very, very good at encoding the dimensions of similarity. In fact, when people kind of started doing this, they realized they were much better than expected. And people then, so once you have this kind of vector representation, it's very interesting to kind of start doing vector maps on these kind of embeddings and see what you can pull out. So, for example, this is a kind of a similarity or conceptual type operation here where x is the word vector that corresponds to pair, and so we can see the singular, the distance between the singular and the plural of words tends to be the same. Okay, so or similar. It's not exactly the same. It's very, very similar. So what we're finding is that the distances between concepts is telling us something that it's actually showing us that these embeddings represent concepts that are, similar concepts end up in a similar place in this word embedding space. And this allows us to do this kind of conceptual type operations. So you can see here, this is a kind of a more sophisticated type query here where we're finding the relationship between chair and clothing is the same as between chair and furniture. Right? And again, this is just based on simple Euclidean distance between the two vectors. A very interesting application of this is machine translation. So what people found is that if you train or if you learn these word embeddings, then the distance between the vectors, and again this is, so what I've done is collapsed this, I think 300 dimensional space down to 2 dimensions, just so you can see it. But what you find is that the distances between the vectors in English, so here these are the numbers in English. If we look at the embeddings that we've trained using the Spanish language, we find that they actually occur in very, very similar locations in space. Right? So what we find is that, again, this is a clear demonstration that we're pulling out with these embeddings, we're pulling out a semantic understanding of text. And we see that by seeing that not only the distances but the relationships between these concepts is the same, and it carries through different languages. So people are using these kind of concepts of numbers the same way in different languages, and we can pick out that from these word embeddings. And again, the basic idea here is that we go from these word vectors, which are encoded in our vocabulary space, to some sort of vectors in a real dimensional, much lower dimensional space. So distributed representation of words can be learned from various neural network-based models. So the simplest ones, the ones that were developed, thinking around 2000, 2001, very simple feed-forward neural network models. Recurring neural network language models have also been used. So again, this is from a paper that was written in 2001 where they kind of laid out the basic architecture of the neural network model that could learn a language model. It's very, very simple. So we've got the input here. These are the words. These are the context. Why doesn't it point to the screen? These are the context of the word. So in this case, the word that we're trying to learn here is WT. And then we have the 3 words that are just in front of that word. So what we're doing is we're learning, we're projecting it through some sort of a layer. There's another hidden layer here, and then there's the output that our neural network is learning. Again, we train this by passing it lots and lots of text. So where you get the text from is kind of up to you. People use things like Wikipedia, they use Google News data sets. You just need lots and lots of English text to train these networks with. What was found, so this was kind of a nice idea in about 2000 or 2001, it was found to be quite unfeasible, so people hadn't developed the techniques for training them very efficiently. These took, I think, weeks to train. They were very, very slow and very, very inefficient. So I guess when kind of Word2Vec, so Word2Vec was developed by I think this Czechoslovakian guy, at least I'm corrected on that. Czechoslovakian, was it? Nikolov? Yeah, who now, or I think went to work for Google. I'm not sure if he still works at Google. And I guess in combination with a number of other kind of developments, things like hierarchical softmax, negative sampling, which was one of the key developments of the Word2Vec paper. They kind of found that they could also remove the hidden layer when they were training it. So in conjunction with a couple of slightly different types of architecture and a few kind of smart techniques, they found that they could actually train these models much, much quicker. So they kind of got an additional speed of about 1,000 times. So this kind of suddenly turned these techniques from kind of a curiosity into something that was instantly very, very useful. And people started using then Word2Vec for pretty much everything. So now there's Word2Vec, there's Sense2Vec if you're using sentiment, there's LEA2Vec, there's something you mentioned before, which is kind of combining with topic models and so on. And again, there are two kind of architectures for Word2Vec. So you've probably heard of the continuous bag of words and the skip round approach. They're kind of inverses of each other. The continuous bag of words is predicting the current word given the context. And the skip round is doing kind of the opposite. So it's predicting the context given the current word. And again, there are some differences in how they're trained. There's some differences in the performance and the efficiency. The skip round approach works well with very small amounts of training data. The continuous bag of words seems to be a little bit quicker and often gets better accuracy as well. And again, the point here, and one of the reasons why we're kind of interested in it, is that this kind of represents the flow from your input corpus. So again, this can be anything. It could be reviews, online reviews. It could be news articles that you're feeding into your system. It could be anything you wish. You're then using Word2Vec. You're getting your word vectors, and then you're building some sort of insights on top of that, which often involves some sort of semantic or conceptual relations between concepts. That's very interesting to do. And you can kind of see from the evaluation here how they went from the initial kind of very, very basic neural networks, basic architecture that took months to train on quite a small amount of training words, to kind of state-of-the-art Word2Vec here at the bottom, which takes minutes on 1.5 billion training words, and it also gets much, much higher accuracy, 72% accuracy. And this is on, I think, a data set where they're asking syntactic and semantic questions of the data. And they're measuring the accuracy. And again, you see there's kind of nothing really close to this. These are all various different types of neural network models. So again, this is another reason why people are interested in these techniques. They're fast, they're very, very accurate, and they're easy to train. You can train with lots of multi-text. And again, this is another reason why we're very interested in for recommender systems, because we can do kind of operations with concepts. So you can see here that the vectors, for example, king and queen, this is again a famous example from the Word2Vec paper. The relationship between king and queen is the same as between man and woman. So this kind of gives us a clue for how to use these word embeddings, these word representations to do operations with concepts. So for example, verb tense. So you can see the relationship between walking and walked is the same as between swimming and swam. You can also get relations out of it between country and capital, so you can see that they have the same kind of distance between the concept space. And people have tried to figure out how exactly do you, so again, there's no theory. This is again just something that people have noticed. There's no real reason why this should work. And there's no direct mapping between these word representations or these word vectors and actual concepts. It just happens that if they're in a similar place in the word embedding space, they tend to represent similar concepts. So for example, you can rearrange this kind of simple vector difference to find the vector that's closest to the one that you wish. And again, people use different metrics to do this, and they get different answers, and some are maybe better than others. For example, bigger in this case, big minus bigger is the same relationship to colder and cold. You can see the relationship to Paris and France is the same as between Rome and Italy. And if you subtract Google from, or Microsoft from Windows, and now Google, and you get Android, So again, these represent very, very interesting ways of looking at these word representations. So when it comes to things like recommender systems, we're interested in asking questions, for example, of hotels. You know, what happens if you take, you know, a hotel that is rated 3 stars for something like room quality, and then add in the representation or the word vector embedding for another hotel that has, you know, maybe a better room quality or is closer to an airport. And you can then find the closest hotel in your word embedding space. So you can do very, very interesting operations on things like concepts that are important for things that involve you know, user profiles or things like concepts. That's very, very interesting to us. And again, people have found that, in fact, if you combine them using multiplication, you tend to actually get more accurate results. So again, here, the two on the top above are things that you should maximize, and the one on the bottom is one that you should minimize. So again, there are many ways of combining these word vectors. You may combine them in different ways and get different accuracy. So this, again, if you're using this concept algebra, this is something you should check and evaluate when you're using it. So I had to go beyond words. So again, we've kind of, word2vec is focused on words. I guess on top of words there are then sentences, and then there are paragraphs, and then there are documents. So it turns out to be a very difficult problem to go beyond to learn the kind of higher level structure. But people have tried. So one thing they've tried to do is to actually go down to the character level. And this was quite a recent work, 2011. I think there's a more recent paper where people have tried to build a deep learning network which actually looks directly at the characters themselves. And apparently what they found is that they've actually found pretty accurate results, that they can actually learn the language model directly from the relationships between the characters themselves. Again, they're using convolutional neural networks to do this. And what they reckon is that you don't actually need, so breaking text into things like words and sentences or so on, it's kind of a high-level structure, feature engineering that you're actually passing into your model. But if you look directly at the characters, the spaces are in there too, so the sentence structure is all in there. So why shouldn't a neural network be able to learn the whole structure of text just from the characters itself? And the results are actually promising that you can do this. So maybe language models are not even necessary after all, and so a whole field of work where people have spent decades developing language models could be entirely at the window as well. So again, recursive neural networks. So here we're kind of looking at this, kind of the lead into sentiment analysis. One thing you find is that the structure of the words actually determines their meaning. The structure corresponds to meaning. So what I'm showing here is that the top sentence, eat sushi with tuna or eat sushi with chopsticks. The difference here is whether it's the difference between a verb phrase. So in the bottom case, it's actually an instruction is a verb phrase, eat sushi with chopsticks. Right? So again, if you just look at the text, you wouldn't necessarily understand that these were completely meant in a completely different sense. And people, again, have spent a lot of time and work developing dependency parsers which can actually understand the deep structure, the grammatical structure of these of text. To do this, and I think it was work that was done mostly in Stanford. I think also Google's the recent Google Syntax Net. They also tried to learn these kind of deep representations, these deep structural and syntactical representations directly. And work that was done in Stanford was actually using a recursive neural network to learn sentiment. So what you can see here, so this sentence is, this film doesn't care about cleverness, wit, or any other kind of intelligent humor. So you can see at the very end that this phrase here, any other kind of intelligent humor, is actually starting off, that phrase itself is actually labeled as a positive sentiment phrase. But because it says at the start here, it doesn't care about, it's at this point that it flips it then over to a negative sentiment. Okay, so this is a case where you've got to understand the structure of the sentence, the actual structure of how the words are put together, and what they mean in order to understand what the sentiment of the sentence is. It's no good just to look at the words and understand that they're a positive sentiment or a negative sentiment word. You've got to understand the structure. The reason this is hard, so again, these are some examples from, I think from music reviews. Sentiment analysis generally gets it gets tricky, so I didn't dislike it, but I was disappointed I couldn't come up with something more. So again, understanding what people are saying, particularly when they use things like negation or sarcasm or irony, is very, very difficult. This is a hard job for sentiment analysis to do. You can see here that the Stanford neural network, recursive neural network, which is trained on movie reviews that come from Rotten Tomatoes, actually does an extremely good job at sentiment analysis. So you can see here we've got one sentence, it's just incredibly dull. It's finding that that's actually a negative sentiment. And then if we reverse it, it's definitely not dull, and it also gets that correct. So the results here at the bottom was basically the state of the art and the recursive neural network that was trained on the sentiment tree bank at Stanford. And you can see it's getting the highest level accuracy, beating the state of the art across the board. So, kind of extensions of these networks. Again, I think it was work that was also done in the Stanford group. They looked at what exactly word2vec was doing, and they found that they could map it to matrix factorization technique. And so they kind of came up with their own word vectors, which is a different way of representing word vectors, which they claim does the same kind of thing. They call it glove. People have also looked at things like paragraph vectors and document vectors to try and kind of pull in higher level or more contextual semantic information. And that kind of work is ongoing. So these are quite recent papers, 2014. There's a few more from 2015 as well. And again, this is something that Facebook are doing. So Facebook have just released, I think this was just yesterday or just today, Facebook deep text. So they want to do things like intent detection, again, based on people writing status updates. You know, for example, if you say, I just came out of the taxi, that they should realize you don't actually need a taxi to be booked for you. Whereas if you say, I need a ride, then maybe you do need a taxi, and so they can kind of pop up a suggestion or a recommendation for a taxi service. And again, they've built a framework which you can use directly. And one of the great advantages, I guess, of the kind of deep learning models is that they can incorporate pretty much any features of different kinds. So they can incorporate definitely the text, but also the images. So if you've posted an image, or there's some audio, or anything else in your status updates, that information can be incorporated directly into the model and learn in the same kind of way. So again, this is the kind of power of the deep learning approach, that it's completely independent of what you throw at it, the format you throw at it. You don't have to understand what the features are. Again, then that's just some implementation. So there's kind of thousands of implementations of these kind of techniques at all different kind of levels, from actually building the neural networks yourself to applying them. So GenSim, for example, will actually do really good things like topic detection, really good word2vec implementation in Python as well. So this certainly doesn't aim to cover the whole breadth of tools that are out there. And again, if there's any questions.